with the presentation? Okay.
I will do a brief introduction first.
Okay.
Welcome everyone to today's INQA online seminar. And it gives me great pleasure to introduce today's speaker, who is Eneko Osaba, who works for Tecnalia in their QTech group in the Basque Country. And Eneko will be talking to us about quantum for logistics, solving real-world bin packing and package delivery routing problems using quantum annealers. So, Eneko, over to you.
Okay, thank you very much for this introduction. Okay, as Paul has said, I'm going to talk about two different use cases that we have already solved in a project with a logistic related company. So one is going to be related with the bin packing problem, and the other one is an ad hoc logistic or routing problem that I'm going to explain later. First, as I have said, this presentation is about is contextualized in a project which is called Q4Real, Quantum Computing for Real Industries. It's an autonomic project, a local project in the Basque Country here in Spain, and with these partners that are using there: Multiverse, Mercedes, the University of the Basque Country, Sericat, which is the partner in which we are working for these use cases, and also Tecnalia, among others. So it is funded by the Basque Country. So I'm going to start first with the use case about the bin packing problem. It's an hybrid approach for solving real-world bin packing problem instances using quantum annealers. It's a use case that we have solved with Erhard Sericat, which is a partner also of the project. And our main motivation for solve this problem is that today, even in 2024, the packing of items into different bins is a daily task for a lot of industries. So the thing is that even it is an old problem, today is a problem that it is solved by many industries, many companies. So the context about this problem is that depending on the characteristics of both the items or the containers, we have different kind of bin packing problems. The problem, as I put here, is generally known as bin packing problem. For example, we have the one-dimensional bin packing problem if both items and containers are described just using one dimension. So mainly this problem, the one-dimensional bin packing problem, is used usually for benchmarking, for benchmarking different kind of optimization solvers. We have also the two-dimensional bin packing problems, in which we use two different dimensions for describing both items and bins. And the application is mainly, there are different kind of applications, but the most known one could be the additive manufacturing. And finally, we have the three-dimensional bin packing problem, which is the most nearer to the industry. It is used for pallet loading, air cargo, and as I put here, it is the one that is fits better with the industry. It is the one that we are going to focus in this first part of the presentation. And the thing is that the three-dimensional bin packing problem, even this problem, has many different variants depending on the characteristics that we have also to describe the items and the bins. The most basic version of the three-dimensional bin packing problem just contemplates the dimensions, just the dimensions. But we have created a wide variety of variants if we contemplate different constraints for the problem. But for example, load balancing or priorities or fragility of different kind of packages. So depending on the real world characteristics, we can build different kind of three-dimensional bin packing problems. Okay, if we want to solve or to work with in quantum world, in quantum computing, in order to solve these three-dimensional bin packing problems, we have different alternatives, but the most efficient one today is to work with the Leap Constrained Quadratic Model solver of D-Wave. There's already one preliminary or one basic library which has been implemented by D-Wave, and this is the one that we used as starting point. So this is the reference code for us. This reference code provided by or implemented by D-Wave is an excellent starting point, but it has a set of opportunities that motivated us to make this research, okay? So the first one is the efficiency of the code, because the reference version code is a basic version, is just to demonstrate how the basic version of the problem can be solved, but mathematically it can be improved. So we have made a lot of work in order to make this code more efficient, in order to solve bigger instances and in a better way. And most importantly, the opportunity that these reference codes provide to us is the applicability, because the reference code is oriented just to solve the most basic version of the three-dimensional bin packing problem. It just contemplates both package and bins dimensions. So it is a good problem, but it is very far from the real world, because it doesn't contemplate features such as weights, fragilities, or incompatibilities, for example. So our objective, our general objective with this research is to build a framework in order to solve realistic instances of the bin packing problem, with the objective of use it in the field of transportation and logistics. So we have contemplated different, as you can see here in this slide, we have contemplated different kind of constraints, such as, of course, the dimensions, the weights of the packages, affinities and incompatibilities among different kind of categories, preferences for package ordering. All these things we are going to see briefly then in some slides, and also in a brief demonstration that I'm going to do. So the thing is that how we have make this. Okay, we take the reference code and we have extended the mathematical formulation of the problem, the CQM mathematical formulation of the problem. Okay, I can talk about this mathematical formulation, but I think that maybe this is not necessary for this presentation. I'm going to go right this way, straightforward to show how it works. Here, I'm going to talk about the input and the output. The input is in this slide. In the left-hand side, we can see one instance of the problem. First, we need to specify how much bins we have, which are the dimensions of the bins, the maximum weight, and other restrictions. And we need to specify to the solver which are the characteristics of each of the packets that we want to store in the bins. And then the output in the right side is a text-based output. This one, the one that we are seeing here in the slide, in which we say, okay, which is the objective value, the weight that is accumulated in each of the bins, and also the position of each bin. But in any case, we have also a more output based on images, in order to be more to easy the visualization of the solutions. For example, I'm talking about the restrictions. I'm going to talk first about the incompatibilities restrictions. Okay, we have here now in the slide one instance composed of 54 items without any kind of restrictions, but we can say to our solver, okay, I want to apply incompatibilities. I want that these blue and yellow packages, they don't need to be stored in the same bin. Also for the yellow and the red packages. So the solver can, as we can see here in the right part of the slide, how the solver has store all the packages in 2 different bins, and it has respect these incompatibilities. We have also, for example, fragility awareness restriction, in which, for example, here we have one instance with 52 items without any kind of restrictions, and in the right side, we can say, okay, this wine color, this dark blue color packages, and the red packages are heavy ones, so they should be in the bottom part of the bin, or in the making a tower of this kind of heavy packages. We can see here how these heavy packages are in the beneath, in the lower part of the bin. We can say also, for example, to this tool, we can say, okay, load balancing, center of the mass. Okay, I want to all the packages to be gravitating around one center of mass, and it could be or the center of the bin or one of the other points of the bin. This is also one of the restrictions that we can say to the solver. Or also, in very important and real world thing is, for example, the heterogeneous bins. We can say to the and here we are also seeing that we can solve 3-dimensional bin packing problem and also 2-dimensional bin packing problem, and using bins that are of different sizes and also different weight restrictions. We have also, this is very important for logistics, for deliveries. We have also the possibility to say to the solver to contemplate delivery priorities. Okay, for example, we can say here, okay, put please the red packages near to the door of my truck, because these packages are going to be the first ones that I'm going to deliver to a client. So I want to open the back door of my truck, and I'm going to take these packages first. So the solver can do it also for you, and if you specify this in the instance. And lastly, before I'm going to make a live demo, this is like a real world oriented restrictions. This is 2 instances in which we, of course, because if we want to solve real world package being package problem instances, we need to contemplate different kind of restrictions. So these are 2 instances in which we contemplate a different kind of restriction. So I know that maybe some participants, some attendants want more detail on the mathematical formulation. For example, we have different articles published. The first 3 ones are in 2 different journals, and also in one top quality conference about intelligent transport systems. All these papers are open access. So I encourage any attendant to reach to these papers. Here you can find the mathematical formulation, for example, that we have implemented, or we have formulated to solve this kind of real world instances. And now I'm going to solve a demo. I'm going to run one instance. So let's see. Okay, this is the problem. I'm going to launch, because sometimes it takes a little bit time in order to solve the problem. The input of the that we need to make to the solver is, okay, where is the instance, the file in which we have the information about the instance, also which is the output, where all the outputs is going to be dropped, also the time limit, mostly important, okay, the API of the wave, and the problem type. If you want to solve a 1-dimensional bin packing problem, 2-dimensional bin packing problem, or 3-dimensional bin packing problem. In this case, we are going to solve this instance, which is the maximum number of bins is 3. These are the different dimensions of the bin. The weight is the same. The maximum allowed weight for each bin is this one. And this relative positioning is the one in order to say the fragility and also the delivery priority. For example, this one is, okay, the packages with the ID 8 should be beneath the packages with the ID 0, for example. And also we have here incompatibilities. Okay, the packages with the IDs 1 and 2 and the packages with the ID 1 and 3, they should not be packaged in the same bin. And here in the last part, we have all the packages with the ID, the amount of packages for each ID, for each class of packages, and the dimensions and the weight. Okay, usually it takes some time because it's a complex problem. So usually the wave put in a queue, but we can wait a little bit for the solution, or maybe I can start with the next use case. Okay, this is prior to the solving of the problem. This also shows which are the variables and the constraints of the problem. So we can see here that the problem is quite demanding. There's a lot of variables that it should be taken into account in order to respect all the restrictions of the problem, and also the variables and the constraints. So it's quite a demanding problem, but even in this case, the quantum solver can solve it. So, okay, because it is taking so much time, I'm going to start with the second use case, and then I'm going to show the results when I finish the explanation of the second use case. So, okay, the second use case is related to a real-world package delivery routine problem. So this is a use case also that we have developed with Erha Serikat, which is a partner in this project, in Q4Real project. And this use case has been modeled by a logistic company called Air Transit. So the objective of the problem is to optimize the cost of delivering. We have different kind of orders and a fleet of trucks, and we want to deliver in the system. It should determine which trucks among the fleet must be used, which are the routes to follow for each of the trucks, and what are the packages, what are the items or the goods that are loaded in each of the trucks. So there are different kind of restrictions. Each truck and the items or the packages are measured in terms of weight and dimension. So we have two different aspects to describe the items and the trucks. We have also a fleet composed by own trucks and rental trucks. The thing is that because of financial restrictions, so the company wants to prioritize own trucks. Why? Because the rental trucks incurs in an economical cost because of the service provided. Also, a single client could have more than one delivery. And this almost last restriction is maybe the most important one, is that they are priority deliveries. So there are some clients that they can see, okay, I want my package to be delivered prior to before the 10 o'clock of the morning, for example. And the last restriction is that the driver must not work more than his working hours. So how to proceed? Okay, this is a very complex problem. What we want to do is to solve it contemplating all the restrictions and using quantum computing. So we have started we define an iterative process in which we are going little by little solving each one of the restrictions. So we started with the most restrictive constraint, which is the priority delivers. And the main objective of the problem is of the sub-problem is to visit as much as possible clients prior to the visit of the most priority delivery. For example, we have here in the left part of the slide the warehouse in which all the fleet of vehicles is. And for example, we have this client. This is a top priority client in which we need to make the delivery before 70 minutes. Okay, and the trip between the warehouse and this client is just 30 minutes. Okay, so we can say, okay, what we can do is visit as much clients as possible prior to the visit of the most priority client, of course, respecting the this time window that the client has established. And then when we visit the client, we have this first subroute. We complete the complete route, the regular route, by visiting all the remaining clients. Okay, so how we have solved this problem? Okay, we have solved using also CQM, because the mathematical formulation that we can use for this in this solver is very very advanced, so we can contemplate a lot of variables, a lot of very difficult constraints. So we have used also the CQM solver of the wave, and we have built an iterative solver that it mainly solves three different kind of routes: the two priority subroutes, the to the pod subroutes, and the last ones that the ones that we have called no priority routes. So some examples about this kind of routes. For example, if we have the instance that we can see in the left part of this slide, we have an instance with 14 different deliveries. So considering that this delivery, this one, is top priority one, so the first part of the solver, of the first phase, in the first step, we are going to calculate a two priority subroute in order to attend the demands of the client before the time windows ends. Then we need to go back to the pod. So we calculate a to the pod subroute in order the track to go back to the warehouse, also visiting more clients. So then when we have built these two subroutes, we build the complete route. And what we are going to do with the rest of the clients, okay, we are going to build, because there are no more top priority clients, we need to solve a regular route, a no priority route, in which we visit all the clients, minimizing the distance of the route. So the main objective function of our problem, in which the quantum computing, the problem that the quantum computer solves, it has two different objectives. The first one is to maximize the number of the packets delivered prior to the visit of the most restricted client, and to minimize the cost or the distance of the route. So different demonstrations. For example, we have here an instance composed of 14 clients. We have, in this case, two top priority clients, the two ones that we cannot visit in the same route because of time restrictions. Okay, so first, the solver, okay, build a two priority subroute, then returning a to the pod subroute, then completes all the regular route, merging the prior calculated two subroutes, and the rest of the clients. Okay, first we need to visit the remaining top priority, the top priority client. Okay, building another two priority subroute, and then we close the route with a to the pod route. This is one of the instances. So this is one instance, and which is the solution that our solver provides to this problem. And for example, a very demanding instance for our solver, this one that has 29 different kind of clients with no priorities. Okay, in this case, our solver also can build 4 different routes, complete regular routes, in order to solve the problem. Okay, in this case also, we have a paper that are in review in Scientific Reports Journal, but it is openly available in archive. So if any of the attendants want to know more about this use case, you can read the paper, you can read it. If you have any question, you can send a mail to me, and we can talk about this. And now we are going to see another demo, but first we're going to see if the solver, yes. So returning back to the bean packing problem, okay, the solver has already finished. So we have different kind of outputs. The first one is this one, which is the text-based output that I have explained before, but probably the most interesting one is this interactive solution, which is a HTML that we can open. We're going to open. It is here, okay? And we can see which is the solution to the problem that our solver has found. This is, we can play with this solution. We can see how the packages have been introduced or have been stored in the bins. And we have developed another script in order to facilitate the visualizing of this solution, in order to see the solution slide by slide, in order the workers can make this solution to be real. So we have implemented this solution viewer by slices. We are going to run it. It's very, very fast. Okay. And this is going to create, I think that 4 different HTMLs files that we are going to see now. It's quite slow today. I don't know. Okay. So running this script, we have here 4 different HTML that are the same solution, but in this case, we can see it slide by slide in order to slice by slice, in order to facilitate the visualization. For example, the first slice is this one, and now the solution is going to be built little by little. For example, this is the first HTML, this is the second one, the third one, and the fourth one. So as you can see, is how the solution is built little by little in order for the workers to solve to make reality this solution. Okay, we are going to change now to the other use case, the package delivery. So I'm going to make also very, I'm almost out of time, but I'm going to run this. Okay, so we are going, in this case, we are going to solve a problem composed by 22 different deliveries. We have, I'm going to show the, okay. We have a fleet composed of 5 different vehicles. These are the characteristics of the vehicles: the maximum allowed weight, the maximum allowed dimension, and the last one is the price of using this truck. In this case, if the truck is an own one, it is of the companies, the cost is 0. But if it is a rental truck, the last of these values are the price of using this truck. So then we have the coordinates. These are the latitude, longitude, in the geographical location of each of the clients, of the deliveries. And finally, we have the characteristics of each of the clients. These are the characteristics of all the packages. Okay, so for example, the client 1, it has a package which has 30 kilograms, and the dimensions are also 30. So now the solution is being calculated. We are going to see how. Here we have created a folder for dropping the solution. This is first the geographical location of all the clients and the pod. Okay, it's opening. This is the pod. These are all the clients. And now, little by little, the solver is building the different kind of routes. So first, because this is a top priority client, first the solver has built this subroute, then it has built this one, and the other clients are well, this is another subroute in order to attend another top priority client. The closing to the pod of the subroot, and the final, okay, and this is the final subroot that is a regular one. So then it comes back to the warehouse. So this is the subroots calculated. These are the complete roots, similar to the ones that I have shown in the presentation. So this is one of the roots. This okay. This is another one of the subroots, and this is the last one of the subroots. And also we have provided a text-based output in order to see all this information in a text base. Okay, so this is the first of the route. It is conducted by the first of the vehicles. This is the overall cost of the route, the accumulate weight, the accumulate dimension, and the three different routes, the characteristics of the three different routes, and also the total, which is the total cost of this solution and the total weight and the dimension. And okay, I think that that's all from the presentations. Just to finish, just some spam, sorry about this, but for all the audience, if you have, we are organizing a special issue in the Journal of Supercomputing, which is a Q2, which is very related with these use cases, which is a special issue called Exploring the Application of Quantum Technologies to Industrial and Real-World Use Cases. In case you are interested, there are the call for papers. And we are also organizing a special session of quantum computing for machine learning and optimization in a conference which is called IDEAL 2024, and this is also the call for paper. So if you have any paper you consider that it can fit in this special issue, special session, you send a mail to me and we can talk about it. And that's all for my side. Thank you very much for attending, and if you have any question, I am very glad to answer you.
Great, thank you very much, Eneko. A little round of applause on behalf of the entire audience. And as Eneko says, we now have some time for questions. So if anybody in the audience has questions, either raise your hand on the Zoom app or just unmute and speak up. Daniel, do you have a question?
As I said, if any of the, I can share with you these slides, and if it's there any questions, you can check the different papers that we have in archive or in published in the journals or in the conferences. So you can check it, and if you have any question, you can send a mail to me. I'm very glad to answer any question.
Daniel Goldsmith, did you have a question?
Yes, I do. Thank you very much, Paul. So thank you, Eneko. It's a really interesting talk. I think I learned a lot listening to it. The first question is, you said that you use the D-Wave Leap Constrained for the bin packing problem. Could you remind me, is that a pure quantum annealer, or does that call hybrid in the background?
It's a hybrid. It's a hybrid. Solver. The Leap CQN solver of the wave, it builds a different kind of threads, and each of the thread is composed by a quantum module and a classical module. And in an iterative process, each of the branches solve the problem. And then the solver provides the best solution found among all the threads created by the solver. But the answer is yes, it is an hybrid solver.
Okay, so I mean, it could have been that it was just solved by a classical solver, and that the quantum annealing ran and it was discarded because it ran more slowly or had a better or lower quality of solution than the classical solver.
The thing is that the CQN solver works. So first, the classical part of each thread solves the problem, and then the quantum module refines the solution, taking different subparts of this solution and making different kind of refinements. We have not made any comparison about our methods and a full classical method. This is future work, because it is quite complicated to make a comparison with a full classical method because the problems are ad hoc made for an ad hoc use case. We need to implement the classical method. There's no one classical method online or already implemented to solve to use it straightforward. So it takes time. So we have planned it as future work. So at this moment we have not any comparison with pure classical solvers.
Thank you very much. Thank you. Thanks,
Sure.
Eneko. Thank you, Paul.
Thank you.
Are there any other questions?
Hello. Hi.
Who is speaking?
Hello. Hi.
Well, Richard, go ahead.
Yes. Hi. How you doing? So my name is Richard. I'm from CNIS, and I've been actually working on very similar topics about route scheduling for autonomous vehicles or even airborne drones for package delivery. And I've been also trying to solve the problem using quantum annealers. And from the previous question, I know you just said that you haven't done any comparisons between your solver and the purely classical one. And I was wondering if you did any comparative studies between, say, for example, D-Wave and other types of annealers. For example, the ones manufactured by fixed stars amplify, for example.
No, at this moment we have not made any other comparison. Of course, we know that because when we publish these papers in the journals, one of the comments of the reviewers is also the same. Please compare it to a classical solver or to another quantum-based solver. At this moment, we have not made this comparison. It is for the future work. First, we have focused on solving the problems using this D-Wave-based approach, and of course, we know that it's interesting. We have planned it as future work, but of course, we know that it's that it would be very good for our research to make this comparison.
Right. Sorry. Just to add very quickly, because I currently also have an article with a similar topic under review at the moment, and I have actually tried to compare, for example, D-Wave with fixed star amplify on some of the traveling salesman instances, and from what I can see, fixed stars are a bit more consistent than D-Wave, but of course fixed star is completely classical. It's what they are calling a completely digital annealer, they are calling it, and the solution quality, at least for the instance that I've tried, seems to be at least on par with D-Wave solutions, if not better, and slightly more consistent.
Yeah. What we have to do for the package delivery, and you can find in the paper that we have in archive, is not to compare the overall solution of the problem, but because finally what the quantum computer does is to solve iteratively all the subroutes. What we have done is to compare the solution of or the performance of the quantum computer solving this subroute. We have compared this with our tools of Google. So and in our case, the comparison is quite satisfactory. So in case we want to solve this subproblem or this subproblem using the CQM or the overall tools of Google. So this is the comparison that we have made, and you can find here in the archive. This is the classical quantum comparison that we have made. Of course, it is better to compare the solving of the complete problem, but because we don't have at this moment, we have made this preliminary comparison with our tools.
Right. Okay. Thank you very much.
You're welcome. Thank you.
Any other questions for Eneko? If not, let's thank Eneko again for a very interesting presentation. Thank you very much.
Thank you very much for all the audience and also to you, Paul. Thank you very
And
much.
I look forward to seeing everyone at the next INQA seminar 1 week from now, which I think is going to be also from Spain.
Yeah, Kilimanjaro.
This time from Catalonia, and it'll be Ana Palacios.
Yeah.
So I look forward to seeing you all then, and thank you very much, Eneko.
Thank you very much to you.
Bye-bye. Bye-bye.
Adiós, muchas gracias.